So welcome back. In today's video, we're going to look at our first container class, and we'll be looking at the bag.cpp. This is the one you've been looking at in lectures, and I've taken my example today from the textbook. So the bag.cpp is going to hold an array of unsorted items. It's going to include functions for handling those items, so we're going to be able to insert items, we're going to be able to erase them, and we're going to have some query functions where we can find out how many items are in the bag and how many instances of a specific item are also in the bag. Then we're also going to overload a couple of the operators. We're going to overload the plus equals so that we can take the contents of one bag and add them to an existing bag. We're going to overload the plus so that we can take the contents of two bags and return a new bag that contains the contents of both bags. And we'll be overloading the cout function so that we can print the contents of a bag. So when it comes to actually making my bag, the very first thing I want to think about is what kind of items is my bag going to hold? In my case, I want it to hold integers. So the very first thing I do is I go through and I say, okay, well, my item type is going to be an integer, and I'm using a typedef to do that. So just as a little demonstration as to why I want to use typedef, let's say we have a look at this implementation over here, and this one I haven't used a type definition to define that item. All I've done instead is I've declared an integer array, and then when I'm erasing items, I'm taking in an integer to find out which item it is I want to erase. When I'm returning an item from that array, I'm just returning an integer. In this case, let's say somebody came back to me and said, you know what, I want that for doubles now. Okay, so I would have to go through every instance of integer and start changing it to double. Not only that, I would actually have to check the context. So down here, oh, I better change that. Yeah, okay. So obviously our data type has to be a double now. I would then also have to check the context. So in this case here where I've got an integer, well, that was actually meant to be an integer. That's not referring to a data type. That's referring to my array index. So I'd still need that to remain. Then I'd have to go through my bag.cpp, and you can see here this is all integers, so I'd have to get it to update to match the new .h file, and I'd also have to go through the implementation and just make doubly sure that everywhere I'm making a temp int or something, it shouldn't need to change to a temp double. I think you can appreciate just how tedious this kind of process would be. So if we go over here, and let's say in this case where I'm using typedefs and then I'm just using that type definition to define the item wherever I need it. In this case, let's say, okay, they come back and they say they want it to work for characters. Okay, so I just type in char. There we go, it's going to flow through the solution. Let's say I want it to work for doubles. Sure. There you go, it's now doubles. So as you can see, it's just much easier to maintain if you're using typedef. It's a really useful little function, and it's a good idea to start using that when you're defining the types of data structures that you're going to be using. So you may have noticed I'm also using a new data type called size_t, and I'm getting access from this from the standard namespace, the std namespace, and I'm also including the C std library to get this item. This data type is preferred whenever you're working with like your natural integers, your 0 and positive integers. So the size of an array will never be a negative number. The reason why we're using it is, let's just say in this example, we were using like an integer to define our capacity, and we were using an integer to define the number of used items. That's all well and good, but integers allow for negatives, meaning that half of the space available on your machine for the integers, or half of the allowable space for integers in C++, is going to be taken up by negative values, which you're never going to use. If you use the size t data type, what you're going to find is that you get double the amount of space available because they've taken what would have been reserved for the negatives and added those to the positives. So you can have much larger data structures by using this size_t data type. So one thing to watch out with that size_t data type is I've redefined that here. So I'm taking it from the standard std namespace and I'm redefining it as size type inside my bag. Everywhere in the CPP that I'm referring to that size type, I also have to quickly make sure that I say yep, and I'm referring to the bag's implementation of that size type. You'll notice I've got it in a couple of places. So down here again where I'm returning the size type, you can see that I've got the bag implementation of that size type. It's just something to watch out for when you're using this feature. So the last thing I wanted to look at is our static member constants. These we're going to set up at runtime and they're going to be available throughout the duration of the program or the solution. So it's for anything that you need to remain that constant value. Some of you might recall these as being similar to like global variables if you're from Gen 1003. If you're from Sen 1110, these are similar to your final, static final kind of variables that you've used before. So essentially this one is capacity, and then everywhere I need it, I've just gone through and used that throughout the implementation of my bag. Now, I've only used it in the .h file to define the capacity here, but you'll see in my implementation, pretty much all of my assertions are around this capacity item. The thing to watch out for when you're using these static member variables is that you need to redeclare them here at the top. So you just go through and redeclare it in your .cpp as well as over here. The final little feature I wanted to show you from the implementation, just by itself, is that I've also included general assertions as well. So assertions can go pretty much anywhere in your solutions, wherever there's a really clear Boolean kind of condition. So in these cases, I knew that I had really clear Boolean preconditions. So if I go over to my bag.h and I look at all my preconditions here, you can see they're all to do with the size of the bag being less than that of the capacity before you can actually do that function. So in this case for insert, I needed the current size of the bag to be less than the capacity. So that just tells me really clearly that, good place for an assert. To use the asserts, I've just needed to make sure that I include the CAssert library up here. So you'll be able to get the implementation code for this bag, the .h and the .cpp from within your textbook. If you wanted to make a copy of this yourself at home, I strongly recommend that you do. It's a pretty good example for getting your head around early data structures. The only thing I've done differently is I've got a couple of extra functions. The first one is this overloaded cout function. Essentially, I'm just trying to print out in set notation the contents of the bag. So I open with this curly bracket and I close with the curly bracket. Then I just use a loop to go through and print out each element of the bag. If I'm not at the last element, I'm appending a comma. So just here, I'm appending a comma between elements. If I am at the last element, all I'm doing is just getting that last data item to print. I've included this get data function as well. You can see it here. And this is literally just going to return whatever item is at that index that gets passed in. So they're the only things that I've done differently or implemented differently to the textbook. So if we just want to take a look at our bag, what I've done in my main just to test it and test if it's working is here I create a new bag and it's an empty bag and then I print out the details. So you can see here that's it happening there, and this is the printing of an empty set. Then I just insert 10 elements into the bag. Once I've inserted those items, I then just go ahead and print that out again. So here, then what I'm going to do is remove an item from the bag. The first time I'm going to attempt to remove an item that doesn't exist. So this is the element 2, and that does not exist with the elements I've inserted. So I'm going to assert that that equals false. If we take a look at our erase1 function, you'll see it returns a boolean. It returns false if we haven't removed the item, and it returns true if we have removed that item. So I do that, and then if that's successful, I then print out the contents of the bag and show that there's been no change. That's just this section here. Then in the last section, I'm going to remove the element 3. Now the element 3 was the first item that was inside our bag. What happens when I remove an element is I take the last element in the bag and I move that to the index where I found the first element. Because a bag is unsorted, there's nothing wrong with doing that. So now that we've been working with pointers a little bit more, what I want to do is look at copying objects just a little bit deeper than what we've done before. So a couple of weeks ago, you might remember we copied some objects on the stack. That was using this syntax here, where we had our object X sitting on the stack, and then we made a copy of it using this notation, and then that gave us our object Y. In this situation, what we're going to do is look at how to copy objects when they're on the heap. So essentially what we've got is an object X, and he's sitting on the heap, and this is what he looks like. First we get our stack address, then that's going to be pointing over to our heap address, and then that's going to have access to our dereferenced point or our dereferenced object. So that's what that's going to look like in the system. If we wanted to take a copy of that object and put it on the stack, we would be able to. We could do it using this syntax here. It's exactly the same as what we did before. The only difference is that we're dereferencing that pointer to get access to the object which we want to copy. So we can do it like this, and we get, we'll end up with an object Y on the stack. In the case that we want to make an object on the heap, a copy of X on the heap, the way we would do that is with this line of code, and this is where we're still declaring an object Z, and we're declaring it to go onto the heap. So we're making our stack pointer, and that's going up to our heap address, and then we're taking our copy of our object X by passing in the dereferenced pointer for X, and that's going to give us our object Z. So what I've done here is I've wanted to take those concepts and just play around with them and make a copy of the bag and amend it and do some things. Here you can see I've created a bag 2 and I've put bag 2 onto the stack. Then what I've done is I've just removed an item from bag 2, and then I've printed out the contents of bag 1 and bag 2 just to check that they are different. In this example, I'm making bag 3 and I'm putting it onto the stack. Using that same syntax that we just saw, and then again I'm removing an item from bag 3, and then I'm just printing out the contents to ensure that those bags are actually different. So in order to copy these objects, what I've been doing is using the default copy constructor. That's provided by C++ for all objects. Essentially, it's just going to take a copy of the object in its current state and create a new object. So you can see here, I haven't needed to define an actual copy constructor. But like everything in C++, let's say that when I wanted to copy objects, I didn't want to copy every single thing from within them. There was only certain elements that I wanted to copy. What I could do in that case is I could define my own copy constructor. So this is my copy constructor here. All it is it's a standard constructor. You just say what the object is, and then you make sure you pass in an instance of its own object. And then over in your CPP file, you can actually just define what you want copied out of that object and how you want that copy to work. So for this implementation, you may remember that the copy constructor wasn't the only way we could go about creating new bags from existing bags. We also overloaded the plus operator so that we could take the contents of bag 1 and the contents of bag 2 and then create a new bag from that. Now, if we take a look at our CPP for that, we're going to create a new bag, then we're just going to add the contents of bag 1 to it, and then we're going to add the contents of bag 2 to it, and then we're going to return it. What you might notice here is that in this implementation, we're being very vague about whether the bag is going to be on the heap. All we're doing is working with a new bag object. We're not defining it in any other way. If you take a look at our main, we're leaving it up to the programmer to decide how they want to implement it. Let's say we're in this condition here where we've got bag 1 on the heap and bag 2 on the stack, and this is the condition we're currently in. If we wanted to create a new bag on the stack, we would have to use some kind of syntax like this. So you can see we've got our normal stack declaration for bag 3, and then we're just getting the contents of bag 1 and bag 2. The result of that is that we would have a third bag on the stack that's going to be made up of the contents of bag 1 and bag 2. In the other example, let's say we wanted to put the bag on the heap. Well, the coder would have the ability to do that too. They'd simply do the heap declaration for the bag, and then they'd state that it's a new bag, and then it's inside the brackets here, the argument, which is where you'd say, okay, but it's going to be the contents of bag 1 plus bag 2. And that's where we're going to get that overloaded operator. So here you'd end up with something that looks a little bit more like this, and the bag 4 would have the contents of bag 1 and bag 2. All still pretty simple stuff, but in practice it can be a little bit tricky to play around with. So the very last thing we're going to look at is a little bit more memory management. You'll notice that as our data structures get more complex, we're going to have to start managing that memory, which is on our heap, and we're going to have to start releasing it when we no longer need to use it. So we use the delete option for items on the heap, and you can see here I'm deleting bag 1, bag 3 and bag 5. Bag 2 and bag 4 are both on the stack at the moment, so I don't want to delete those. In order for this deletion to work, I have to actually define how it's going to work. So to do that, I simply create a destructor. That's my destructor there. Pretty simple. You just put the little tilde character, and then I go in here and I make sure that I delete all of the data that is in this object. So that is my implementation of a destructor. So that's the end of having a look at the bag.cpp container class. If you do have time, I'd strongly recommend that you do have a go at implementing this. You can find a lot of the implementation code from within your textbook. It's a really simple data structure. It's a really good one to start with, and it'll just be really helpful if you do have a go at making your own bag. And good luck.